All right, I hope everyone can see my screen. And so with that, we'll get started today. Today we'll be continuing some of the Python tutorial. We'll be going over control flow today, which is very similar in Python as it is in many other languages that you've worked through, but with a few more eccentricities that we want to cover before we move on to NumPy. In May, we will have our NumPy tutorial, and then with the tutorials we have, that should give a pretty good foundation for the Python and Heliophysics summer school, which is towards the end of May. So with that, we'll just note that all the notebooks that we're going through can be found on GitHub. You can launch them in Colab, or you can launch them directly from Colab using the GitHub. And we have additional resources on our website, some new ones that I'll go over today at the end of the lecture.
Kyle, the link isn't public for the notebook.
The link is not public for the notebook.
Yeah, people aren't able to get to it. Or some people, I think, they're saying. Oh, Kyle, I just added the public one. The link I think you shared was the one you're using.
Okay, so the new one works. All right, yes. Perfect. Thank you, everyone. We'll get that updated on GitHub later today. So what we want to go over today is basic control flow within Python. So your if statements, your for loops, your while loops, functions, and we'll talk about some more interesting aspects of Python, in particular exceptions, which are quite helpful in dealing with error messages that you can get within code. And then we'll also talk a little bit about variable scope. So depending on what language you've used before, you probably have an idea of what variable scope is. However, if you've used or are really familiar with IDL, the concept of variable scope is a little bit looser. So we'll go over that here today as well. So the if, then, else, for loops and while loops, they're very similar in IDL or in Python as they are in any other language. One of the biggest differences, though, is that instead of using braces or parentheses or statements to define the beginning and end of these control statements, Python uses indentation or white space. Now, this is quite ideal. It makes code much cleaner. So within something like C++ or IDL, you can program a loop without ever using proper indentation. So this can make code quite messy. And so the nice thing about IDL is that with this control or defining of a loop within a control definition of a control statement using white space and indentation, this forces really clear, consistent code and generally makes it much easier to read. The one key thing, however, though, is despite having this indentation, you'll still want to comment your code. That's always really important. And so if we start off with the if, then, and else statements, these are very similar to any if, then, or else statement that you have within any language. You're going to have a condition within the initial if statement. If that condition is true, or if it matches that condition, you'll execute that block of code. You can then use an else if statement to do another condition, or you can just print an else statement. So if no condition is matched, we're going to do what is within the else block of code. And so if we look at the code cell here, we have a very simple if statement. Let's look at the variable a, which we'll set initially to equal -10. And we'll just do different things within the if statement, depending on what the value of a is. So if a is exactly equal to 0, we'll print 0. If a is greater than 10 or less than -10, we'll say that it's too big. And if it's less than 0, we'll also say that it's negative. If it meets none of those conditions, then we'll execute the final block of code here, which is the else statement. And so if you notice after the definition of the if, we have the condition, and then a semicolon, a colon. And that defines that the next line is the block of code within the if statement. And that's our indentation here. Our else if is aligned with the if, and then anything within that block of code is indented. And then finally, our else is still aligned with the if and else if with the code block indented. Note that this final line here is just an arbitrary line. It's not indented, and so it's out of this entire block of code. And so if we run this with a equals -10, what we'll find is that we are within the bounds. So a isn't equal to 0, it is greater than 10 or less than -10. And so we get else in here. Our final one is just an example if we want to run a few more things. And one of the things that is nice here is that we can play around and see how small a needs to be before Python thinks it's 0. And so unlike many languages, it can be it requires quite a small number. So if we say 1e to the -350 and run it again, Python thinks it is 0. But if we say it to the -100 and run that cell, it still thinks that a is within bounds. And so this is just something to bear in mind within the memory when we're working with Python, is what is actually 0 and when the interpreter will think that something is bigger or larger. So things to try: play around with a and play around with the values of a to see how big or how small a really needs to be before it's 0 in Python. So if and else statements, they're kind of very similar. Again, biggest difference is that white space and the indentation to define them. With the while loop, it's also very, very similar and to any other language that you have. A while loop will continue to run as long as the condition is true. The big difference between a while loop in Python and some other languages is that it has an else statement at the end, or you can use an else statement at the end, which is often overlooked. So once the condition is matched as false, an else statement within a while loop will be executed within that statement. So here we just have a simple summation. We can say a is initially equal to 0. We can define a total variable that is also equal to 0. And as long as a is less than 10, we're just going to add 1 to a, and we're going to add a to total. And so if we run this block of code, we get what we typically expect. We have a going down the left, the total going down the right, and then we have the final sum, which gets executed once a is greater than or equal to 10. And so this is a very simple while loop. It's typical to the while loops that you've usually used in other languages. The big difference is the else statement here, which can come in really handy to signify the end of the loop or to do a final bit of processing once the loop is finished. So if we move on to for loops are probably the biggest difference in Python compared to other languages. In most languages, when we're using a for loop, we iterate over some value that corresponds to an index within a data set. So if we're working with arrays, we typically start with the initial index of an array and work towards the end so that we can do some sort of manipulation on the array. In Python, however, our for loops actually work over what is called an iterator, or a data type that is iterable. And what this does, instead of passing an index, we actually iteate over, say, a list, and we grab in each instance of the for loop the value within that iteration. And so that is the biggest difference, and it actually comes in quite helpful. It generally makes things much faster, and it allows for easier manipulation of a data type. And so an example here is the for loop at the beginning of the line here. Here we've defined a list of values just arbitrary random values. And what we do is we can specify that we want to iterate over this list with the value I corresponding to each iteration with the list, starting at the first index and going to the last. And so instead of defining the index that we want to run over, we can access this element and then sequentially all the other elements. And so if we start with this, we can run it very easily. This is quite simple. We have a generic if statement. If I is less than 10, we say we're good. If not, we continue. And so all we do is print each iteration within this list, starting within the initial sequence, going towards the end. The other nice thing about the for loops is it also, like the while loop, has an else clause, which will print if the for loop finishes its full execution. If it doesn't finish its full execution, then we won't actually go through the else statement. And I think we'll get an example of that later on. So like lists, we can iterate over numbers or values, but we can also iterate over any type within the list. As we went through in previous examples in our initial tutorial, we showed that a list can be a list of strings, a list of integers. It can also be mixed type. So here we have the very similar loop. This time our list is a sequence of strings, HDZ, and we can iterate over W with the variable S, and that'll just iterate over each indentation here. So fairly simple. We can do the same thing with dictionaries. Dictionaries, if you recall, had key value pairs. So the initial portion of a dictionary was the key. The colon separated out the value for that key, and we could have different sets of key value pairs within a dictionary. So like the other two, a dictionary, or like a list, a dictionary is still iterable. And so for a dictionary, we can loop over all of the keys within the dictionary and then access the values for that key using a simple for loop, which is for K in the university dictionary. So this dictionary is just a simple dictionary. The key is California. We then have a number of universities within California. And then the second key is Alberta with a number of universities in Alberta. And so if we run over that, what we see is that for the first key, we get California, and we can print the key with K, and then we can access the value of that key by using the uni dictionary with the key value there. And that prints out the values at the end. So now in addition to accessing a dictionary through the keys, we also have a method for all dictionaries, which is the item method. Do proper typing. And so if we access the items within a dictionary, this will access each set of key value pairs. So instead of looping over just the keys, we're actually going to loop over key value pairs. So instead of having K, we also want to add a new variable, which will have the values of it as well. We're going to define this as V. So now we have for K and V in each item of the dictionary, we will print K and V. And that'll give us the same output. I think I have a typo. I think it's items. There we go. So just incorrect function or method. And so for each of the items, we just print out the key as well as the subsequent values. Now, when we are accessing data, often we're accessing different arrays which are a similar size or a similar type. And so we might want to access, say, if we're looking at a time series of solar wind velocity, a time series of BZ, and a time series of density, all which are stored in a different array. Now, Python still has a functionality where we can loop over a nominal indice, and we can do that using the built-in range function. So if we know the length of the arrays that we want to work with within Python, we can access each row or each column of array using this simple range. Now, this is generally much slower, and one of the powers within Python is the iterables. And many of the data types that will come up in NumPy or Pandas or SciPy, which will be talked about in the future, or which you will likely be working with, will have built-in iterables, which will make this much faster than accessing an array via index. However, if we look at this, we can generate a set of indices which increases by 5, which is our second last element here. And this generates indices from 5 to 100, not inclusive of the final value. And so we can use that range function to define a set of indices to work with data arrays if necessary. Now, if you do have iterables, instead of working with the indices, there is a way to loop through different iterations or sequences of multiple data arrays. So if we look at, say, our initial array that we had, W, which was an array of strings, and X, which is an array of numbers, we can actually loop over both of these without using without using indices in a similar way that we kind of did for a dictionary. So we can say for I and J in, and then we can use the zip function, which is a built-in Python function, which will combine these two lists together. And so we can say for I and J in WX, and then we can print both I and J. And so if we run that, what if this for loop will do is it'll iterate over each element of W and X, which we've zipped together and printed out. So that's another way to avoid using indices in Python and instead use the built-in iterations, which are generally much faster. Now, like many other languages, Python also has control statements. And so control statements are helpful within while loops and for loops in order to skip over an iteration or in order to exit out of the loop in case something happens, in case you reach some line of code that you don't want to run. And so these are the generic continue and break statements. So the continue will move on to the next iteration before doing the rest of the block of the code, and the break statement will completely exit out of that loop. Now, I mentioned before that this else statement that we had within a for loop and while loop, it only executes if the loop is fully executed. And so if we use a break statement, what we'll find here is that if we break out of the loop before finishing all iterations within the list here, our else statement won't complete. So if we run this, we get what we typically expect within a for loop with continue and break statements. If I is equal to 3, we continue. And because we continued, we didn't get any of the print statements. And if we do something similar, if we go here, none of our values were greater than 90, so we never broke out of the loop. But if we create this fourth element to be 100 instead of 10, what we'll see is that when we run this for loop, we don't actually execute the else statement at the end. And so if we run that one more time, we loop through the first 4 iterations. We get to the last one, which is greater than 90. We print break, we break out of the loop, and we never complete the else statement at the end of the loop because the loop was never completed. So I hope that makes sense. For loops are the biggest difference in Python compared to other languages that I've found. But many of the software packages and data analysis and science packages that you'll be using in Python, if you do move to Python, such as NumPy and Pandas, they will have built-in methods for their various arrays, which will allow you to very quickly iterate over them, making it very simple to use iterations instead of indices. And so if we move on, the next big type of control statement within any language is functions. And functions within Python, like any other language, are very similar. They're similar in Fortran and C as they are within IDL and MATLAB. One of the biggest differences in Python is that Python is an object-oriented languages, and so all of our functions belong to a class like C++ or Java. And so with that, we can define certain methods within each of the functions that we have, but they will also come with inherent methods. Now, the other thing I want to quickly touch on is within Python, you can add additional functionality, which we haven't touched on too much yet, by importing packages. And so for the next few examples, I'm going to import the math package, which will allow me to do some very quick math on some of the examples in the next little bit. We'll talk a little bit more about packages in the next tutorial. We'll be learning about NumPy and packages in general. There are a couple links here that'll help to understand packages and how to install them. Python generally has very good documentation, and so do the large data analysis packages. And so there's excellent tutorials as well as excellent doc sites for essentially all packages that you would want to use, and excellent documentation for installing these packages. In addition, there's a little bit more about reading up about different package managers. If you're using Anaconda, you'll generally be using Conda to do most of your packaging and installation for different Python packages. But there's also an additional package manager called pip, which you will sometimes use to install packages which aren't part of the Anaconda environment. So let's have a look at a very simple function that we can program within Python. We'll just look at calculating the square root of a number and returning that square root within a variable call or within a function call. So here I'm going to import the math library so that we can use the square root function from the math library. I'm then going to define a function using the def statement and then the name of the function. Within the parentheses, we define the variables that will be passed to the function, and then start the function with a colon, much in the same way we did with for loops, if statements, and while statements. Now, if you notice here, everything that is indented after the def statement is the body of the function. And so that indentation in white space, again, defines different blocks of code within Python. The 5 sets of lines here, which start with 3 quotations, this is the doc string of the function. And so this tells a user what is happening within the function or what the utility of the function is. It is also the set of strings or comments that get passed to the interpreter when we call something like help on this function that we're defining. And so it's different from a comment in that it starts at the line right after the definition statement. It begins with 3 quotations. It ends with 3 single quotations. And everything in here is initially ignored by the interpreter, but is compiled into a doc string, which we can access after it's been compiled. The body of the code is here, and what this function will simply do is if x is less than 0, it will return the negative square root of negative x. If it's positive, it'll just return the square root of x. So our for statement here is outside of the definition of the function, as it now starts on a new set of white space and is not indented. And we can just loop through this, and we can print the output of the function for different values within the list, -4, 0, and 4. And so if we quickly run through this, we get something very simple. Our output within the for loop, the square root of -4 is -2, as we've defined it. Square root of 0 is 0, and of 4 is 2. We do fully execute the loop. So the else statement here does get executed as well, and it just signifies the end of the loop. If we print x2, this is something interesting if we're looking. It is the final iteration, so the variable does still exist, and if we print it, it is now 4. And a final quick note is that within Python, you can call functions within the sequence or by passing variables within the sequence that they were defined in. Or if you know what the name of the variable is, you can call them using x is equal to x2. So this comes in handy when you start working with larger functions, which have more inputs. Now with our function, we can use different help utilities built in within Python to look at what the function does. This can be done with any function, not just functions you write. But if we call help on the my square root function, it tells us initially what it is. But the nice thing is it tells us the name of the function, all the inputs that we have, and then it also gives us our docstring. So this is a really quick way to access what's happening with, or what a function does, what its utility is, and what its input is. So these docstrings are really, really helpful and create a really quick way for people to look at what your function is doing. If we look at a few more examples, we can use the my square root function. Because it's compiled in the cell before, we do get tab completion for it now. But we can also call it with the question mark, which does the same thing as help. In Colab, it just opens a new terminal on the side, which again just tells us what the function is, the inputs, and prints out the docstring for us. Now, finally, with the docstring, you can access it if you want to print it to screen, and it's always stored in the attribute variable __doc __. Now, you don't really need to use this very often. The help function and the question marks are generally a much easier way to get help for different functions within Python, or different objects or different variables. Now, just a little bit more on the function arguments that we touched on briefly. Our square root function initially just took one input, x. Because of that, we can call it in a couple different ways. We can call it with just a value within x, or we can call it within a keyword argument. And so the keyword argument defines the variable from the function call, which is defined in the definition statement. And then we can pass x is equal to 4. If we have larger sets of arguments within a function, this is helpful because we can call functions using these keywords in any order. Whereas if we call them without the keywords, we have to call them within the order that they're defined within the function definition statement. Now, if nothing is passed, we get the default arguments, which is similar to the required arguments. And so we'll define a new my square root function with a couple different keywords or input values. And we can see the different ways that we are able to call this function within Python, which is slightly different than other languages that you've likely worked with. And so let's define a similar square root function. It's going to take a required argument of x. It's also going to have default arguments, verbose and classic, which are initially going to be set to false. So if we don't set these within our function call, they are always going to be false. X, however, is a variable that we are always going to have to pass within this function call. So within this, we're going to import math again so that we can use the square root function. And if classic is set to true, we're going to execute this block of code. We're going to print, and if we have verbose, we're going to print the classic statement on x, and then we're just going to return the square root of x. Else, if x is less than 0, then we're going to apply some fix to our code, or to the input parameter. We're going to do the square root of -x and return the negative value of that. If neither of those are defined, we're just going to use the normal square root function. And so the bottom here shows different calls that we can use. We can say print my square root of -4. And so if x is less than 0, we'll execute this initial block of code. We can specify verbose is initially equal to true using the second line here. So we'll do the square root of 2 with true. And then the final block of code will execute the square root of 2, but we will force it to execute the classic or the classic version by using the true statement. And so if we run those, we get what we typically expect. The square root of -4, based on our statement, we execute this block of code, and we get -2. The second one, we are doing verbose. So we are printing the initial verbal, or we are printing the verbose statement, which is correct here, and we get 2. And the final one, we're just printing out the square root of 2 here. Now here, we're going to do something quick that will break our code. If we say my square root is -2 and we want to do classic, we're going to execute this initial block of code, and we're going to try and calculate the square root of -2 using the math function. What we'll see is that we initially run the first 2 lines of code, but what happens is that we get a value error on the second line, or on the very last line here. And that's because the math square root function cannot calculate the square root of a negative value, which is why we were fixing the code here. Now that comes in helpful, and that kind of brings us to our next set, or the next part of the tutorial, which we'll talk about error handling. And so exception handling within Python gives us a way to test something out, determine whether it works, and then continue on within the code, or to do something else. Now, in many many languages that we have, if we run a block of code and we get an error or an exception, that typically stops the code from executing afterwards. In IDL, if we get an error, an exception, the code stops on the line where we got it. And in compiled languages, generally, if you get an error or exception, the language won't compile. Or if it compiles, you will get an error statement. Now, IDL as a nice way to address this, which will let you handle exceptions using a block of code, which is the try and except statements. And so this is really helpful because within code, if you don't know what your inputs are going to be, if you're reading in a file and for some reason there's a blank line that you're reading in, and you might get an error when you're trying to fill variables with that blank line. Conversely, if you're trying to run, say, a Fourier transform on something, on an array or time series, and it has not a number in it, you might get an exception. And so these try and except blocks of code are a really nice way to run your code, and if you get an exception, do something else and continue on. I found them quite helpful, mostly when reading in data from different files. If file lengths tend to be too small and we don't have an entire day worth of file, this try and except, or an entire day worth of data, this try and except will allow me to try and read in a file. If it's not big enough and I get an exception, skip it and move on without the code actually falling apart. And so here, we can do the try and except statement with our last block of code when our square root function failed. So within the try, we start the block of code with try and then colon, and then we use an indent to specify what we're going to do within this try statement. So initially, we're going to try and print my square root is equal to -2 using the classic value. If we get an exception, we're going to do and exit this other block of code. And here, we're just going to say we had some error, and we're going to try and deal with it. So if we run this, what we find is that Python tries to execute this block of code. It gets an exception, so it stops here, goes to the exception block, and starts doing here. So as I said, I found this really helpful within Python. You can try and do something. If you're in a loop and something fails here, instead of your code falling over and not continuing within your data process, you can add a break statement within your except or a continue statement to move on to the next iteration. And so it's a really nice way to keep your code flowing even when it comes into handling something that you weren't expecting. Now, the other thing you can do is you can define the type of exception. So depending on what type of exception you get, you can do different or execute different blocks of code. So if we go up to our last statement, what we found was within the my square root minus 2, we were getting what was called a value error. And so we can actually define within our exception block of code what to do if we come across a value error. And so a list of exceptions within Python can be found here. And depending on what you're working with, you can mostly determine what type of errors you might expect. And you can set up your code to do to execute different blocks of code depending on those errors. And so we'll just run through a really quick example here. We're going to do a try statement. We're going to print sum underscore new underscore variable. We're going to try executing our block of code, which was the square root of minus 2. And then we have two different except clauses. If we get a value error, which we were getting for our function with a call to minus 2, we're going to print some error. If we get a name error, we're going to print this line of code here. And so a name error is what happens if a variable isn't defined yet. And so within this Jupyter notebook, we've never defined some new variable. And so within this try statement, we're going to try printing a variable that doesn't exist, and we're going to get an error. Now, within the try statement, as soon as we get an exception, we exit the try block, and we moved to the except block that matches the error that we get. If we haven't defined the error, we go just to the blank except block. So if we run this, we initially get a namespace error because some new variable hasn't been defined yet. And so we execute the except block with a name error. Now, if I comment this out, and if we run it again, we skip the some new variable, that's not done, but we can do the my square root again, and that was a value error. And so now we're exiting the value part, or the except block of the value error. And so like I said, well, within Python, I find this really helpful. It's a way to help continue moving data processing along, even if you come across something unexpected. So the final thing that I want to go over today is variable scope. Now, depending what language you started coding with or what language you typically use, you might have a really good idea of what variable scope is. If you've used IDL, sometimes variable scope might be a little bit more fluid than it is in other languages. And so I think it's important to touch base on what variable scope is within Python. And so within Python, if we're running something within a function, typical variables within a block of function are not visible outside of the function. And so if we were to define a variable within our square root function, that variable wouldn't be available to us outside of that square root function. And so there's a couple examples of how that might work here. And so we're going to define two different functions in two different examples. We're going to look at initially a set of global variables and local variables. And so global variables are ones that we do define to be accessible everywhere within our block of code. Local variables are only accessible within the function that they're defined in. And so in the first example here, we're going to define a variable a1 equal to 1. We're going to define a function called test a, which takes one input x. And we're going to make within that function, we're going to call the keyword here global a1. And what that will allow us to do, that will allow us to access the variable a1, which has been defined outside the function test. We can print a1 plus x, whatever value we pass to the function, and we can change the value of a1 by saying a1 is equal to a1 plus x. And so if we go down here and add a print statement as well, we can initially run it and test 2.0. We'll print A1 plus 2, and then we'll change A1 to A1 plus 2. And if we run that, what we find, A1 initially starts off at 1, we add 2 to it, it's now 3, we add 2 again, it's 5, and if we print A1 outside of the function call, we note that A1 is now 5. So global variables, if we define them within a function, allow us to access variables which are outside the function. Now, what about local variables? Local variables are variables which are defined within the function, which aren't accessible outside of the function. So if we define another function or the similar function here, we'll redefine test A as X. We'll do the same printing, but we'll now make a variable Y that is equal to A1 minus X. Now, if we run the same thing, we can do test 2.0, test A 2.0, run it twice, but then we can see what happens when we try and call Y. And if we run this simple block of code, this gives a good intuition of what the local variables are. And what we see is that when we initially call it, it runs fine. A starts off at 1, we add 2 to it to get 3, we add 2 again to get 5, but then we try and print the variable Y, which is defined within the block of code within the definition of the function. And what we see is that we get a name error, and that name error is because Y hasn't been defined. And that's because Y is outside or is inside and is local to test A and is not available outside of the function definition. So that's everything that we have on control flow today. Like many languages, the control flow in Python is very similar to what it is or to what you expect. The big difference is the for loops and the iteration, which come in really helpful. As you work, or if you start working with Python and moving to NumPy and pandas, there's a significant amount of documentation about how to iterate over the different data sets that those packages provide to you. And then the other big difference is the try and except statements, which are quite useful when you're trying to run a large data set or trying to run analysis on a large data set and might be expecting to come up with some errors. It's a really good way to have your code continue to run, even if it, for lack of a better word, hiccups on some iteration of your analysis. Now with that, I want to just make a couple quick announcements. I want to remind everyone about the Python in Heliophysics Summer School. That is going to be from 30th of May to Friday, June 3rd. It is in Madrid, but it is also virtual. It's free, and following our next tutorial on NumPy, you should have a good foundation in Python to work through this Heliophysics Summer School, which will be covering packages including AstroPy, SunPy, SpacePy, PlasmaPy, and several others. You can link to it. You can see the blog at the summer school at HelioPython here, and you can register to the school at the school for the first link here. We do have some additional resources which people might find helpful. There's a series of lecture notes in the SciPy lecture notes available at the link here. This will provide an additional foundation to what we've gone over, as well as goes over NumPy, Matplotlib, and pandas, which could be helpful before the summer school that we won't be able to touch bases on. Finally, there's an excellent resource here, which came from the SpacePy webpage, Mathosaurus, and this is a really good, succinct set of documents which link different languages together and show you what a function call or what a variable definition in Python might be, and the same thing in R, IDL, and MATLAB. So if you are used to using IDL or MATLAB, this Mathosaurus page is a really good resource to show you what you've done in IDL and how you would do that in Python. Final two announcements. There is a special issue on Python and space physics. If you are a Python user, and if you have a package that you use all the time, I would suggest that you run over to this link and see if you might want to write a paper on your package. And finally, we have no seminar next Monday. Our next seminar will be on April 25th, and we will have Andrei Runov discussing the dynamics of the magnetotail. So with that, if anyone has any questions, please feel free to put them in the chat. And if anyone has any comments, you can go to the comment page or that Barbara has set up in order to provide us with feedback, but also ideas of what you might want to see next within this Python and computational tutorial. So thank you.
That was marvelous, Kyle. We did have one question earlier. I think it's been resolved about when you assigning versus testing, equal or double equal. And so if you accidentally put equals in a loop, I equals 3 instead of I equals 3, it does throw an error. However, I equals 3 is a test which can return true, and I equals 3 is an assignment. And so there are some cases where in your code, if you don't, that both will work. And so, yeah, there you go. Yeah, so it returns, so A equals 3 is, it does return a variable, it does return a value. So there are some cases where you can, where that can mess it up. But fortunately, Python is usually polite enough. So if at least if it's expecting a condition and you've given it an assignment, it tells you, no, I don't know what you're doing here. So.
Yeah, and so that's actually quite helpful. So we get invalid syntax if we try to use a non-conditional within the if statement. However, we can assert something in order to determine if it's true. And that is still sometimes helpful depending on what you're doing in code. I've used something like A is equal to 3 if I want to determine the type, and only do something if the type is particular. So if I'm working in pandas and I'm working with a data frame, I might use something like this to determine if the data frame is empty, if it's full, and then determine what I want to do to that data frame based on whether or not it's full or empty. So these statements do come in helpful still within code, even outside of these control statements.
Yeah, they're also nice for making masks if you want to, because then you can make an array of zeros and ones that you can feed into something. So you can feed in a subarray of something just using a mask, which is created by a conditional. And that happens a lot in image processing. So it's very handy. So so next time you're going to learn about NumPy. And NumPy has a lot of built-in functions that take the place of loops, because instead of having it go iterating through each one individually, it vectorizes it. And so NumPy handles arrays. It has something called an array, which is similar to a list, but it has a lot of it has functions and arithmetic operations that allow you to kind of go through, or algebraic operations that allow you to go through and manipulate it. But yeah, this looks, everybody seems to be okay I'm not seeing any more questions. Does anybody have any, do any of our expert panelists want to have any things they want to share?
All right, well, with that, I want to thank everyone. And for those that have Easter, I hope you have a wonderful Easter weekend. For those that don't, I hope you are at least able to experience spring within the next couple weeks. So have a wonderful week, everyone.